So our first objective here is to recognize the functional anatomy of the somatic nervous system and the neuromuscular junction. Now, as we talk about the somatic nervous system and the neuromuscular junction, I really want you to be drawing contrast in your mind to differences, important differences between the neuromuscular junction and the neuroeffector junction, okay? Again, not compartmentalizing this, but really connecting it. What is different or what distinguishes the NMJ from the neuroeffector junction, okay? All right, so let's start off by speaking about the anatomy of the somatic nervous system. Now, before we get into the anatomy, in your mind, you should already be distinguishing these two systems functionally, okay, functionally. The neuroeffector junction and the autonomic nervous system is responsible for unconscious functions, blood pressure, pH, things that we're not aware of. The somatic nervous system and the neuromuscular junction is responsible for conscious movement, okay, movement of skeletal muscle. So everything here is under our conscious control, is under our voluntary control, okay? So please bear that in mind as we talk about this. Now, the anatomy is such that we have motor neurons. So unlike the neurons that we saw in the autonomic nervous system, these are differently named and they arise from a different part of the spinal cord. Does anyone remember where the neuroeffector neurons arise from or arose from? Not the dorsal, very close though. So that's the area of the spinal cord, but in terms of the cross section, which of these areas, which of these horns, or not the ventral, this arises from the ventral, the lateral horn, perfect. So the fibers from the autonomic nervous system come from the lateral horn. The fibers in the somatic nervous system come from the ventral horn, okay? Very, very important distinction to make. So they arise from the ventral horn. They exit on that motor neuron and they make their way to skeletal muscle, okay? Now they innervate many muscle fibers and together they create what's called a motor unit, okay, a motor unit. The only neurotransmitter that we see in the somatic nervous system is acetylcholine, okay? Only acetylcholine. Therefore, we only see cholinergic receptors in the somatic nervous system, okay? Very, very important. And we only see nicotinic cholinergic receptors. So only those fast receptors, okay? And that speaks to the fact that the somatic nervous system needs to be a very fast response, okay? It needs to be immediate because these are things that we're controlling, okay? We can't wait until tomorrow or in an hour to move this limb. Like if I want to move this limb, I need to move it now. So we only see these fast receptors in the somatic nervous system, okay? Very important distinction to make. So let's look at the motor unit. Now we said a motor unit is a single motor neuron and all the fibers that it's innervating. So if we look at this schematic here, we can see motor neuron 1 in blue, motor neuron 2 in red, motor neuron 3 in purple. Now each of these motor neurons, as we can see, is going to more than one fiber. I don't know if you guys are familiar with the anatomy. We'll talk about the anatomy of muscle, but a muscle belly has several muscle fibers in it, okay? And so one neuron going to more than one of these fibers is considered a motor unit. However, each muscle fiber can only be innervated by one motor neuron. Okay, this gets a bit confusing. So one motor neuron innervates many fibers, but one fiber can only be innervated by one motor neuron. Okay, so let's take this fiber here, this red one, okay? If we zone in on this fiber, it can only be innervated by one motor neuron. It cannot receive innervation from motor neuron 2, 3. It can only be innervated by one motor neuron. Alrighty? All right, so let's talk about what happens at the neuromuscular junction. Okay, so we have the activation of a motor neuron depending on the EPSPs and IPSPs that are synapsing onto this neuron. All right, so whatever is happening at the soma, again, connecting from what we know previously, if we have an EPSP, what type of channel will we open up? If we have an EPSP, what type of channel will we open up, likely? Calcium or sodium, right? If we have an IPSP, what type of channel would we open up? potassium or chloride, right? Don't forget that stuff. So based upon whatever type of event we have here on the soma, then we will sum those events and decide whether or not we get to an end plate potential. Okay, so an end plate potential is what we call the action potential in muscle. Okay, very, very important. So the end plate potential is what happens on the muscle to bring about contraction of the muscle. And this happens in response to an action potential or to excitement of that muscle fiber. Okay. Now, so the action potential that's traveling along, that's elicited or started here at the axon hillock, travels along this motor neuron, makes it to the end of the neuron. We have exocytosis of acetylcholine, and that binds on the other side. So we're going to go through those events. But important to point out here is that we have one neuron, we have one type of neurotransmitter, okay, and we have the end plate potential being generated. Sure. So basically the end plate potential is what happens on the muscle. So we talked about the action potential moving down the neuron, getting to the terminal, the axon terminal, exocytosis of that neurotransmitter. We're going to walk through the steps in a bit, but basically when that binds to that receptor on the muscle, what that brings about is an end plate potential. So it's specifically the contraction of muscle that we call an end plate potential, okay? Just like an action potential of muscle, basically. Okay, which is contraction. All right, now, so we have a synapse between the motor neuron and the muscle fiber, okay? At this junction, which is called the neuromuscular junction, we have the terminal bouton, which is the same thing as the axon terminal, okay? We've been using those terms interchangeably. And then we have the motor end plate. So the motor end plate is what we call this highly folded region of the muscle. So the region of the muscle that comes into contact with the motor neuron is called the motor end plate, right? Now we have all of the neurons here releasing acetylcholine. I keep mentioning that just so you don't get confused. There is no other type of neurotransmitter released in this system. The synapses are always excitatory in terms of what happens on the muscle, okay? And then acetylcholinesterase is also a player in this system as well. So let's spend the last few minutes here drawing out what this looks like. Any questions so far? Okay, so we're looking at the neuromuscular junction. And we know this is between a motor neuron and skeletal muscle, okay? So this is our motor neuron. And this is our highly folded skeletal muscle, okay? And we call this region the motor end plate, the motor end plate. Okay? I'll put in brackets here skeletal. All right, so in this axon terminal, we have our very same scenario. So we have vesicles and we have neurotransmitters stored in these vesicles. What is the neurotransmitter here in question? Acetylcholine, right? Only acetylcholine. Okay, and so very much like what we've been speaking about so far, our action potential is traveling in this direction. It gets to the axon terminal. Can you see this? It gets to the axon terminal, and then the voltage change, which excites the membrane, triggers the opening up of these voltage-gated calcium channels. And so calcium rushes into the membrane here. Okay, calcium rushes into the membrane. This triggers the exocytosis of this vesicle, and this dumps all of this acetylcholine into the neuromuscular junction, okay? Now understand, I'm using a little bit different terminology here because there are some specific terms, there are some terms that are specific to the neuromuscular junction, okay? So this dumps that neurotransmitter into the cleft, and again, we have receptors here. Now, what type of receptor is this? If it's on skeletal muscle and it's binding acetylcholine, we know it's a cholinergic receptor, but is it fast or slow? It's fast. Good. So it's a cholinergic. It's a nicotinic cholinergic receptor. Right? And I'm going to put in brackets here ionotropic, just so that we remind ourselves that this is a fast receptor. Can you see that? Why is this up? Sorry. Sorry? Yes, exactly. Nicotinic are ionotropic, muscarinics are metabotropic. Those are synonymous, okay? You can think of nicotinic as the name, whereas ionotropic is describing the way it operates, okay? So that's this type of receptor, which basically means that when we bind this neurotransmitter to this receptor, that will open up some type of channel. Remember, ionotropic receptors are acting as a channel. So the binding here opens up this channel such that sodium rushes in or potassium rushes out. Basically, whatever the channel is, we're going to have the movement of those ions. And that will immediately bring about our response on the skeletal muscle. Now, what did I call the response on the skeletal muscle? Can anyone remember? It's contraction, but specifically, what is it called? What type of potential? An end plate potential, an end plate potential, okay? Right? So basically the movement of ions through this ionotropic receptor, let's say we had sodium rushing in, I'm just gonna draw this here as an example. That would depolarize or excite this membrane. The muscle would contract. We're gonna talk about the events of how that occurs, but basically we bring about an end plate potential in that contraction. And this is how skeletal muscle contracts. This is how skeletal muscle moves. Okay, so very important connection to what we're gonna talk about later on in muscle physiology. Can you guys see that clearly? It looks so blurry on that screen. Okay. Yeah, that's not how, oh, there you go. Okay, magic. All right, okay. Any questions on this? Any questions so far? Any questions? Now, the very same sequence of events that we saw before, we have our Pac-Man type molecule here. This is called acetylcholinesterase. And this is degrading any excess acetylcholine, and that's going to either be degraded and cleared away as it is, or degraded and reuptaken, okay? And I'll put here again choline and acetate so that you know these are the breakdown products. Right? Now, in the case of skeletal muscle, it's very, very important for us to clear the neuromuscular junction, to clear this neurotransmitter away. If we don't clear this neurotransmitter away, this muscle will contract indefinitely. Do you know what the physical symptom of muscle that's contracting indefinitely is? Spasm, right? Muscle spasm. So if we don't clear this neuromuscular junction, we end up with muscular spasms, okay? So this becomes very, very important to clear the junction. Not really, not necessarily, but contraction definitely requires acetylcholine here. Okay, it also requires the appropriate action of this receptor, this cholinergic receptor. Okay, we'll talk about some toxins that block different things here. We'll also talk about myasthenia gravis next time, which is an autoimmune disease that affects this receptor, right? So I think that's it for